All right. 28B. This is chi-squared test. 28B. What page is that on? 534. Okay, number 1. Suppose the same die had been used to generate the tables in 4A and 4C, rolling it first 60 times for A and 600 times for 4C. Can you pool the results of the two tests? If so, how? Can you combine them into one? Do you want to go close that? Could you combine those into one table that had 660 rows? Yes, because they're independent. Do the roles in A affect the roles in B? No. Hey, don't make fun of me. All right, number 2. Suppose the same die had been used to generate the tables in 4A and 4C, rolling it 600 times in all. The first 60 rolls were used for 4A, but table 4C reports the results of all 600 rolls. Can you pull the results into two tests, into one table? So in the first example, in the last problem, we did 60 here and 600 here. And we can combine them because they're totally separate. Okay. The second one, we took 600 and we put 60 of them here and 600 of them here. Now can I combine those into a single value? No, if I wanted to combine them, I might as well just use this table because it already has everything in it. Okay. And 3. One of Mendel's breeding trials came out as follows. Make a chi-squared test to see whether the data were fudged. So, fudged? You like fudged? Okay. So, the first one is observed, and this one is expected. Where did those expected numbers come from? They had to have come from his Punnett square ideas, right? So in all, we need to figure out how many there were. 315 plus 101 plus 108 plus 32. So there are 556 in the sample. And then how many are going to be in the expected? It's got to be the same amount. Right? I don't need to add them up. It's going to be 556. So I need to perform a chi-square test. How do I do that? So I would do 315 minus 313 squared over 313, and then I do that for all of them. So the first one is only off by 2, so 2 squared divided by 313, plus the next one's off by 3, 3 squared, and does it matter which way I subtract? You're going to square it, so even if they end up being negative, they're going to be squared, so I'm just going to find the positive values. So divided by 104, and then the difference between 108 and 10, that's a 4. 4 is 4 squared divided by 104 plus 3 squared divided by 35. And I get a chi-squared value. Uh-oh, that's not right. It definitely shouldn't be that big. Oh, I missed a divide. Right here. So I get a chi-squared value of 0.51. Okay. What do I do with that? Go to A106. How many degrees of freedom do I have? So for degrees of freedom, I eliminate one column and one row, and I end up with 3. So on A106, I go to 3 degrees of freedom, and 0.51 is going to put me in between what? Degrees of freedom, 3. 0.51 puts me between between 95 and 90. So in this case, we were not trying to see if his ideas were working. We're trying to see if they were too good to be true. So where would the too good to be true mark be? At 0.35, right, in that 95% window. So we're just outside of the 95% window, which means we cannot say that it's too good to be true. So most of the time when you do a chi-squared test, so most of the time we're looking for a 5% window over here, right? We're nowhere near that. We're on the other side. But if we end up over here in a 5% window, then we think that the information is fake. It's too good. Right. So over here, we would reject the null and say there's a difference, right? Anything in this window, we accept the null and say there is no difference. But if we happen to land in this window, we pull our trump card and say fake news, right? It's too good to be true. If we were rolling dice and we landed in that left tail 5% window, we would say this is probably not a true dice roll because the numbers are way too accurate. So in this case, it doesn't look like Mendel cheated. But in the other example that we looked at, it said that he did.